Hello everyone, welcome to my show Sizzling Live Code. Today we are going to cook a live code, and what we have today is a programming language Rust, and I'm going to cook a code in Rust, but you need to guess what I'm going to cook. Any guesses? So for you, all of you, the hint is we are going to cook something which has imaginary. You can add it to the comment section. Any guesses? Okay, so to reveal, I'm going to cook complex numbers today in Rust. I'm going to cook the complex numbers today in Rust, and without any further delay, I'm going to share my screen. So I'm using the IDE Rust Rover. Rust Rover was recently released by IntelliJ IDEA. This is going to be a paid tool, Rust Rover, but right now preview is available. You can download it for free. You can preview. It's in a beta. You can preview it. You can use its features. You can try it. The entire setup I have already done so that we don't take much time for setting up things. So what I'm going to do is I'm going to create new project. I'm going to call it complex numbers. You'll see over here I have toolchain, cargo bean, nightly. So there are two versions of Rust which are being distributed. One is stable and one is nightly. Nightly has a latest feature, but those are generally experimental, less stable. So use nightly with your own precaution. So now I'm going to use nightly. Now I have created a new project. You'll see IntelliJ provides a Hello World project by default, and you can directly run it using run markers. You'll see Hello World printed over here, but we are not here to print Hello World for getting started. We are here for trying complex numbers. So what I'm going to do is I'm going to first create a struct. So Rust provides creation of data type called a struct. In this struct, I'm going to have two parts. Real is going to be F64. Now what F64 is? F64 is a float with a 64-bit precision, and imaginary is going to be F64. Now our complex number will have a real part and imaginary part. We don't want hello world. Now what we are going to do is we are going to implement a new function on this complex struct. So that we will be able to create complex number. You will be able to create complex by some syntax like this as well. Like let's say let x is equals to complex real is 1.0 and imaginary 1.0. But this looks so verbose, right? So what we are going to do is we are going to create a constructor function constructor function is going to get two arguments and it will return a self. So self is a special keyword in Rust. Self can refer to a struct which is itself. So this struct is complex itself. So I can say self and I can use self instead of complex also over here. And here I can refer real and imaginary. So what's happening here is like this real is being passed to self and imaginary is being passed to self. What is there in writing code without test? So we are going to write test as well. What I'm going to do is I'm going to create module test. For you, Rust has inbuilt feature for writing test. So for you to write test, you need to define that module as the test module so that it won't be included into the distributions or whatever code you are creating. Now what we are going to do is we are going to write a test the constructor. So what I am going to do is I am going to say fn creation of complex should work. Now what we are going to do over here is we are going to check whether when we create a complex with new, and new 1.0 as real part and 2.0 as imaginary part, same as complex real 1.0 and imaginary 2.0 or not. Now, for this method to work as a test, we need to mark it with the attribute test. You see a run marker available over here. Let's run this test. It's failing, saying binary operation cannot be applied, and Rust compiler itself is giving some error that you need to derive this struct with partial equal. So what partial equal does is it creates methods which will be used for measuring the equality between these two objects, two struct objects. Like this object created by complex new and this object created by complex new, they can't be compared for equality unless they have equality derived. So what I'm going to do is I'm going to derive. So Rust gives us inbuilt macros with which we can derive partial equal. So what Rust will do is it will write code for you which will compare real with real and imaginary with imaginary. Now let's try to run this code. Now this says complex doesn't implement debug. Now assert equals requires you to have the objects with a debug trait. What debug trait means is if something goes wrong, assert equals should be able to print the objects. So we are going to again say that derive debug trait as well. So debug trait will derive how to represent this complex on a command line. Now let's try to run this. And this test is passing. Let's try to fail this test. I'm purposely failing this test so that you know like how it looks like. Because we derived debug trait, you can see it is printed like this over here. In debug mode, the complex number will be printed like this. But for us, this test is green. Let's proceed. So we quickly created a complex struct, a struct which represents a complex number. We can create object of this complex number using new. So what I'm going to do is I'm going to simply say x is equals to complex new be real as 1.0 and imaginary as 2.0. Now let's create one more complex number y is equals to complex mu, be real as 2.0 and imaginary as 3.0. Now what happens when we add these two complex numbers and create variable z? Can we do this? Right? Says cannot add complex to complex. It means this code will not work unless we write some custom code for it. So what we are going to do is we are going to first write a test for it that addition of two complex numbers should work. Now when we say that, what we need to do is we need to create x as complex mu 1.0, 2.0, set y is equal to complex mu 2.0 and 3.0. I'm just creating any arbitrary complex number, and I want to check whether if I add these two complex numbers, it becomes proper or not, proper addition or not. So when we add these two complex numbers in mathematics, the real part will be added with real part and imaginary part will be added with imaginary part. And we want to check it with x plus y. For sure this test is going to fail because cannot add complex to complex, the trait add must be implemented. So this is where we are going to see operator overloading in Rust. We are using operator plus over here to add two complex numbers, two structs actually, objects of two structs. So in Rust, any operator you want to overload, we have a specialized trait for it. Let's see what we can do. So what I'm going to do is I'm going to implement a trait add. You can see this is showing as std ops add. So I'm going to implement this trait for complex. Now when I say I'm going to implement this trait, it is showing me red warning. It means I need to implement the methods which are provided. So I'm going to use features of IntelliJ for fixing the things. Now you can see over here there is a type output is equal to round brackets. Now this round bracket means we are going to have output as nothing. But when we add two complex numbers, our output is going to be complex. So this is a trait with a parameter output, and we are going to define that output is going to be a complex number itself. And over here we need to write a code. So what we are going to do is complex new. Now over here you can see for this method we have self and RHS. What the self mean is the object which is available at the left side of the plus operator. What internally is happening is Rust is calling x.add method and passing y to it. So we have self.real plus RHS.real. We have self.imaginary plus RHS.imaginary. And when we don't have semicolon over here, it means this line will return whatever is the output of this line. So complex new will create a new complex number with its real part being addition of two real parts and imaginary being addition of two imaginary parts. Now let's run our test. Yes, our test passed. It means we were able to overload the operator plus Similarly, we can overload the minus operator. Let's try the first. Let's try to write the first failure test for it. We'll write subtraction of two complex numbers should work. It's going to be minus 1.0 and it's going to be minus 1.0 and x minus y. Test is going to fail because subtract complex from complex, because it says this rate is not implemented. We haven't yet overloaded the operator subtract for complex numbers, so we are going to implement it for complex. Then our output is going to be complex number. Instead of addition, we will do subtraction. So far we have implemented subtraction method and this test is now passing. Now what we are going to do is we are going to print complex numbers. Let's try it in our main method as well first. So we have this main method over here. Let's try to print x, y, and z. X is equal to. Now you'll see there is this question mark symbol. This is a debug. We want to print x in a debug mode. So this is saying that borrow of moved value x. What does that mean? Like when we use x over here, x was moved. Moved means Rust has a borrow checker and x was eaten by this operation. In order for us to not that happen, we will implement copy and clone trait. So what will happen over here is x copy will be taken for this operation and then we will have x for our usage. So you can see x is complex real, but this is not how complex numbers are written, right? So what we are going to do is we are going to write a display method for complex number. We'll say x is equal to, this question mark is displaying in a debug mode and this other symbol, other brackets is displaying in a display mode. So you will see over here Rust is giving us some error that complex does not implement display trait. In order for us to format any structs or variables or anything, they must implement a display trait. Now let's see if we can directly derive display. Unfortunately, displays cannot be derived because Rust assumes that you want to display it in your own style, right? So what we are going to do is we are going to similarly implement a display trait for complex number. When I say I am going to implement a display trait, I need to implement FMT method, which is format method. Now let's put the to do itself over here. Let's try to run this. It's going to fail. It's going to panic. So panicking in Rust means something which is your program terminated in error. So you see main panic not yet implemented because we haven't yet implemented this format. It's required over here. Now to implement it, let's first write a test. Should format complex number. I'm going to say complex x is equal to 1. And I'm going to check whether a formatted complex number. Format is a macro over here. I'm going to check whether if I format x produces string which is 1 plus 2y or not. It won't because we haven't yet implemented. So let's implement it. So Rust gives us an inbuilt macro, right? And what this f is a formatter. We are going to write to f. You will see over here f's reference is mutable. We are going to mutate f and we are going to write something which has we get a reference of self as well. And we are not having a semicolon over here because we want to return this. Now let's see what is the output of our test. We'll see that it has printed, the test has passed, and let's try to run our main code as well. We'll see that x is equals to 1 plus 2y. This is not how complex numbers are directly printed. Let's have our testers pane coming up over here. Complex number. What happens if my imaginary part is 0? Right. When imaginary part is 0, then it will print 1, right? No I and all. But you will see our test is failing. It is saying output is 1 plus 0i and our right is 1. You'll see the difference over here. It means we need to fix this method format. So what I'm going to do is I'm going to write this condition over here. Self.imaginary equals 0.0. If self.imaginary is 0, I can directly print real part without even imaginary part. Now this should fix our this test. So it says mismatch type because we are writing 2 times. It should go into the else part. Let's run our test again. Now our test passed. Any other cases coming to your mind? One case that is coming to my mind is when real is 0. And imaginary is 1. See, when real is 0 and imaginary is 1. What is the output? The I, right? It's like I. Mathematically print it as I. Let's see what output we get. We get 0 plus 1i. It means when real is 0, then we should omit it. So we need to add a condition over here. Else if self dot real equals to 0.0. Now we have one more condition. Then when self dot imaginary is 1, then we don't want to print 1. So what I am going to write is we should print only I. If self dot imaginary, if it is -1, what should it print? Print -I. If self dot imaginary, in other cases, what should it print? It should directly print number and I. We wrote a bunch of line of code, but let's see our this test is passing. Okay, this test passed. -1, -I. Let's see if this test passes. This test is passing. When it is negative, -2, let's say, should be -2I. Okay, so this test is passing. When it is positive, we wrote a test for 1. Let's see when it is positive 2, what happens. Okay, so this is working fine. But when it is 0, what happens when it is non-zero? Let's repeat this test. Actually, in Rust, you can write macros. When you see you are copy pasting a lot of code, I can write this test as a macro, like a parameterized test that we write. But for today, we are not going to have that ingredient in our code. So let's write a couple of other tests. See what happens. It is non-zero. See what happens. 1 plus 2I. It's working fine. Non-zero and imaginary is 1. This test is going to fail. Let's see. Because we haven't coded for this, you'll see that output is getting printed as 1 plus 1I, whereas we want 1 plus I. So we are here under this condition. When imaginary is 0, when real is 0, in else condition we are directly printing. In else condition also we will need this condition. Over here we will print real self dot real plus I self dot real minus I. Over here we have either plus sign or minus sign, right? So we are going to write else if self dot imaginary is lesser than 0.0, then The sign will be directly from imaginary number. And in other case, else condition will have a plus sign over here because imaginary will be positive. And that's it. So let's test this. This test was failing. So this test is passing now. And imaginary real is non-zero and imaginary is -1. Let's see our code is working fine or not for this condition. It's working fine. It's negative. Any negative number. And so in that case, we should have number also in front of it, right? This is working fine. And it is positive. A plus sign in front of it. Okay, it's saying that we have repeated this test. So I think we wrote already this test. First test that we wrote test only. Now let's run all our tests. All the tests are running fine. I'm going to run all the tests with the cargo test command as well. There are 13 tests. All of these tests are passing. And we just cooked a complex number. We only implemented addition and subtraction. But similarly, you can implement multiplication and division as well. You should know how to multiply complex number, how to divide complex number. There are formulas in mathematics for that. You need to take real parts and imaginary part and do mathematics over there. That's how we cook complex numbers. I'll take questions now. There are no questions. So hope you liked today's episode. There will be recording available. Instructions for setting up your Rust environment will be available as a after episode activity. So that's all I had for today. Stay tuned for the next episode. Thank you.